Welcome back. In today's episode, we'll discuss parametric curves and surfaces, or NURBS, as they're called in CAD environments, such as Rhino and Grasshopper. So as you can see, they're already on the screen with an example, and you can see a bunch of curves and the surface. But we would like to define these objects in a more methodic way so that we can reproduce them. Of course, the software does it for us, but we want to understand how the software is doing it and what's behind it. Before we actually see exactly how the software does it, let's try to come up with some solution, because we are engineers. We already know something about curves, right? We know functions. So can we use functions to solve this problem? Well, kind of. So let's see an example. Let's say we have 3 points in our Cartesian system. So let's say this is x and y. Imagine this is the CAD environment. Let's say we have point P1 here, and maybe point P2 over here, and then point P3 right here. Okay, and let's say these are coordinates 0, 0, and this is maybe 2, 1, 2, 0. Okay, and this may be for 2. Okay, and what we want to find, let's try and connect this line with this one. We want to find a curve which starts from this, goes all the way to P3. It's tangent to P1 at the start here, so its tangent here is horizontal, and the tangent here is parallel to this P2, P3 connection line. How do we do that? Well, we could try to solve this with a parabola, because this is sort of like a parabola shape. So let's try to do that with an explicit formulation of a parabola. So we already know what that is. We can recall a generic parabola is y equals ax squared plus bx plus c. And if we find these three coefficients, a, b, and c, we have defined a parabola, and we kind of solved our problem of finding a curve which maps to those 3 points we defined. So let's try and do that. We have initial conditions, boundary conditions, sorry, to find these coefficients. So we can say that when x equals 0, we are here in P1, so we know that y equals 0. So we know that y equals 0. That means that we can write y equals, a times 0 squared, which is just 0, b times 0 plus c equals 0. This, of course, goes away, this goes away, so we already found that coefficient c is 0. And then we have a bunch of other stuff that we know. So of course we know that the curve passes through P3. So it means that when x is 4, then y is 2. So let's do that. So when x equals 4, y is 2. So that means that y equals x is 4. So a 16 plus b 4 plus c. Well, c is 0, so let's not put it in. This equals 2, and now we have a and b as unknowns, so we need a third equation. And we know the slopes, as we said. We know that in P1 the slope is 0, and in P3 the slope is 1. Okay, let's use the first one because it's easier to compute. So the slope is the derivative of the function, so the y first is the derivative. And we can say 2a x plus b, this is the derivative. And we said that when x equals 0, y first is 0 as well. So we can substitute that in. So we can say 2ax, so 0, plus b equals 0. So we found that b equals 0. And since b equals 0, then we can bring it back up here, and we have that, this is 16a equals 2. So this means that a must be 2 over 16, which is 1/8. Okay, so now we have all 3 coefficients, and we can draw the parabola. So let's try to do this same example in Rhino and in Grasshopper and see if this actually works. So let's go back to Grasshopper. Let me delete these 3 example curves. And so Grasshopper, fine. So let's define the first first the 3 points. So let me split the screen so you can see both the space and grasshopper. Okay, so x, y, z points. So we need the x coordinates. We have that they are 0, 2, and 4. Multi-line data, of course. Let's delete panel. Okay. And then we have y. The corresponding y's are 0, 0, and 2. So we can drop them in like this, and we have now the 3 points. And now we want to find if the parabola we found actually passes through those points. So let's try to do that. We will use evaluate. We already explained in the math video how this evaluate component works. So this accepts x as an input. It will give us y as an output. So this is y of x basically. We need to provide a list of x's. So let's define a bunch of points from 0 to 4 with a series component, so that we can compute the y's, the corresponding y's. So this is goes from 0. Let's say the step is maybe 0.1. Okay. And for the count, I mean, we may do the calculation by hand, but let's just write a simple expression. So evaluate again. That actually computes the count for us. So the count will take the maximum of the range. Let's call it mx, and then let's say mn is the minimum of the range. We could call this the domain. The x domain, and then we need the step. Let's call this st, and the function to compute the count is just, well, max minus the minimum divided by the step plus 1. So this is the function. We'll compute it, and then we provide the start, which in this case is the same as the minimum. The maximum, we need to create it. In this case it's 4, and then we can drop in 4, and then the step here, and we get the result, which is the count. We drop it in, and indeed we get a series between 0 and 4 in increments of 0.1. So let's drop it into not the expression but x, and then the expression is the parabola we found, which is y. So y is already set, we don't have to repeat it. It's 1/8, because that was a, times x squared, b0, c0. So this is just our function. So we get the corresponding y's, and now that we have y, we have x, we can just plot them using a construction points. Let's do this with points. So this is y and this is x, and indeed we get the parabola between 0 and 4, which passes through the points, which is quite interesting. Let's try to use the Rhino command for the curve and create a NURBS. And indeed, we're happy about it, because the NURBS is actually represented by a parabola. So what does this mean? Well, it means that the curves that are shown on screen when you use Rhino or any other CAD are actually just polynomial functions, cleverly tweaked so that they pass through points. Now, we made a very simple example with an explicit form of the parabola. This is not actually what the solver is doing. So let's actually make a step further and explain why this formulation of the parabola is not actually good. And one of the reasons is, let's say we had on our CAD environment a parabola drawn like this. Well, this wouldn't be possible in the explicit form, because we would have that for a single x, we have 2 y's, and that's not a function, so we cannot do it. So we need to find a different way to describe these functions, which are not based on x and y, but they're based on the points. Before we get into that formulation, let's solve another problem, which is the one that y and x, that we only have this y and x, and they are we are defining y based on x. We would like to define x and y independently from each other. So let's start tackling that problem. And the way we do that is by, well, making up a third variable, which we usually call t, and it's a parameter. So that's why these are called parametric curves. So let's try to do that. We already have this solution, so we'll use this same example and just write it in a different form. So what we don't like is that y is described dependent on x. So let's say that x instead equals t, okay, and then we can write y with respect to x, so to t in this case. So that would be, well, in general form, a t squared plus bt plus c. All right, and now we solved our problem because we don't have that y depends directly on x anymore. The x depends on t, y depends on t. So if we tweak the value of t, we will get two values, x and y, and we can recreate all the points that describe our parabola. We could find even better formulation. So instead of t, I tried before, so let's use a different one. Let's say we use a 4t, and the reason is we don't want, I don't have the eraser. Okay, it was just small, but it's here. Okay, so instead of just using t, which we would like to have a parameter such that when x is 0, t is 0, and when x is 4, t is 1. So this formulation is very simply 4t. So if t is 1, then x will become automatically 4, which is the end of the domain. And if x is 0, if t is 0, x will be 0 as well. And now we could rewrite the entire generic form, but we already know a, b, and c for this case. So let's just do 1/8. And instead of x squared, we have 4t squared. All right. So this is the formulation using this t parameter. And what t is describing is, you can imagine walking along this curve, and t is just defining a coordinate along this curve. So let's go back to Rhino and use this other formulation to do the same thing. So we will just hide this stuff we already did. We will just delete this. Well, we can keep the points actually because they are the same. And let's use again the evaluate expression. But instead of using x and y, we will compute x as a value of t and y as a value of t. So let's do that. And we can now use an expression. So we know that 4 times t is x. Sorry, this was the expression, not t. And then the y is 1/8 times 4 times t to the power of 2. Okay, that's the y. And then we can drop in any value of t. In our case, we need any range between 0 and 1. So let's copy this one. Let's say the maximum is 1. We will go with increments of 0.1 again. So this is our series for t. Okay, and then we can easily display this x and y's again as points. So let's do x, y, z. So this is x and y. And indeed, we have the same thing, but now we can use this parameter to define how much we are going through the curve. So let me try to say that 0.1 is the maximum. Actually, let me put a slider in instead. So 0.02, let's initialize it as 0.1 to 1.0. So let's see, yeah, correct. And this was the, this was the step. I was wrong. So this is the step. Oh no, actually, that's fine. The 0.1 is the step. This is the maximum value, all right? And now if you increase the value of t, you see we are walking around the curve. And if when t is 0, we don't have anything because we are at the beginning of the curve. If it's 1, we are at the end of the curve. So this t is the domain of the curve. All right, so now we found also how to decouple x and y, but we're still kind of not satisfied because we're still tied to this explicit form of the parabola, and we would like instead to have something which is directly connected to the position of the points and not to boundary conditions that are generated from those points. Can we do that? Well, yes, there's a formulation, a better formulation for it, which is called Bernstein base. So let me go to Wikipedia, and so I'll show you what the functions are, and then we'll implement them. All right, here we are. So this is the formulation of the Bernstein basis. It's just this one at the top with this binomial coefficient. What we actually care about is these examples down here. These are giving us coefficients that we can use to rewrite in a different way our polynomials. In our case, we are dealing with this third line. So these three coefficients will describe a parabola as our a, b, and c instead of a, b, and c. So let me just write it somewhere here so it's clear what the formulation is. So we have that in explicit form, if you will. X equals ax, y equals ax squared plus b x plus c. And instead in Bernstein basis, what we have is that we have what we could say y, but let's say f in general, is a function of point p1. So the first point multiplied by the first coefficient, which we can go back and check what it was, 1 minus x squared. So p1 times 1 minus x squared. Instead of x, let's use the generic parameter t. So 1 minus t squared plus p2, and this p is really a point, as we saw with vectors. So it's point, it can x and y. So these are the actual coordinates of the point stored in vector form. So this is the first the point, and then the basis function. So 1 minus t squared is the first one. The second point is multiplied by the second function, which is 2x or 2t 1 minus t. So let's go 2t 1 minus t, 2t 1 minus t, and then the third point, b3 is multiplied by t squared. You can actually check that on the Wikipedia page. T squared, here it is. This just shows the example for order 0, 1, which is just a line, to the parabola, 3 a cubic, which we'll see in Grasshopper shortly. If you can go ahead as you wish using this binomial coefficient formula, which is, if you click it, it will show you what the binomial coefficient is. It's just using factorials to create coefficients. So these numbers here, the 2, the 3 are generated by that binomial coefficients, and then you have multiplication of 1 minus t times elevated to a certain power multiple times. All right, so now that we know a different form, so instead of this explicit, the Bernstein form, let's try to use it in Grasshopper and see if it actually helps us to draw an easier curve. So let's go and preview that off. And let's write this, the Bernstein basis first. So we said it's 1 minus t squared. The second one, we will write them as vectors, is 2t, 2 times t, times 1 minus t. And the third one is t squared. I hope I wrote them correctly. We'll check shortly. So these are the three functions. We'll do evaluate. So these are the expressions. And then we'll give a certain range of t. Let's use 0 to 1 as we're used to. So we can just copy this one. Okay, so for a range of t's, so this is t between 0 and 1, and this we can put f, just a generic function in. We will get these functions, and we can use a graph. I don't remember how it's called. Let's go to display. There should be a chart preview. Yeah, quick graph. We can use that. So we can drop in x, which is this one, and y, which is that one. Actually, not really. We need to make it first. Actually, we need to provide only the y's. Okay, and fine. And we need to graph this so that we can find three functions. Right, so the first one is the red one, this one over here. The second one is this green one, and the third one is the blue one. So what we're basically doing is we're taking the first function and multiplying it by the position of the first point, the second function, which is that inverted parabola, and multiplying it by the position of the second point, and then use this third function and multiplying it by the position of the third point. So let's define 3 points. In this case, we will do them directly in Rhino so we can easily move them around. Let's start with the same example as before, and then we'll just move them to show you that it doesn't break. It will work for any arrangement of those 3 points. So let's take those points. So P and P and P. Okay, I'll grab them individually so it's easier to make computations on those. So point 1, point 2, and point 3 there. Now we need to multiply the coordinates of this point. So let's take and deconstruct each point. So let's deconstruct the first one like this, the second one like this, and the third one. And then we need to do the multiplications. So let's do, so we need to put them in a structure so we can multiply them by these functions. So we have 3 branches here. We'll multiply the first branch by the x, the y, and the z of the first point, the second by x, y, z of the second, and so on and so forth. So we need to construct this tree if you wish. So let's do x of the first one, the x of the second one, and the x of the third one. So we have the 3 branches of only x. Then we have y. We do the same. Okay, and we could do for z as well, but let's keep it 2D. So let's ignore the z parameter. You can try it; it works in the same way. And then we can do mass multiplication, or actually just the multiplication, I believe. So we can multiply x by the function, so here, and then y by the function there. And then we need to sum this together. So now it's mass addition, so that we get the values. All right, and now we have 3 values for x and 3 values for y. That should be correct. And indeed, these are the coordinates for this one probably are the coordinates for the different yeah, this one. So before doing this, for x, and these are the y's. So we can now take x, y, and z vector and display them. So let's do that like this. And actually, I need to flatten those. All right, so I forgot I had to flip the values. So we do the multiplication of the Bernstein basis times the coordinates of the point. Then we sum the three coefficients, the first, the second, and the third. And after we sum them, we can just well, get a single list of coordinates, so of x and y values, and indeed we get the same result as before. And same as before, if we move the value of t, we get from the first point to the end point. But now if we move these points around, and you can even rotate them, this will work just the same way, because it's based on the position of the points, not anymore on x and y in an explicit form. All right, so this was doing it with a parabola. We can connect if we have, and you see we have 3 control points. So 3 control points means that we use a second degree curve. If we had only 2 points, we would use a 1-degree curve, so a line. We can actually try that as well. So I'll just make a copy of this one and just change the functions here. So let's go back to the line. The line was this second example, so 1 minus x and x. So let's say I have 1 minus t and t. So these are the functions that we multiply, and then we only have 2 points. So let's delete the third one. Okay, and in this case, these are the 2 points. Let me hide the parabola example preview off. So these are the 2 points, and they are indeed connected with a line. Of course, if we select a different point, let's say this one, we still get the same thing. And now the t is going from the first point to the second point. So as you see, this is kind of like averaging out the position between the first one and the second one. And we can otherwise use a cubic example. So instead of a parabola, we could use a cubic. So let's put it, let's read the coefficients. So 1 minus t cubed, 3t, 1 minus t squared. Let's write them. So 1 minus t cubed, 3 times t times 1 minus t squared. And then we have, so 3t, 1 minus t squared. The same 3 with t squared. So 3 times t squared, so 3 times t squared, 3 times t squared times 1 minus t. And then I believe we have just t cubed. So these are the cubic Bernstein basis. And again, we can change between 0 and 1. We need a fourth point because for a cubic we need at least 4 points. So let's drop a fourth point in here. Okay, let's select it. So set 1 point, that one. And we need to add the x to the first tree and the y to the second tree. And indeed, now if we inspect that one and we hide the line, we can see we have a nice cubic. Let's put in maybe a smaller step. And indeed, we go from the first point to the last point. And the way these curves work is that we start from the first one, we get to the last one, and these are not points which we pass through, but they still like control the position of the line. And indeed, we can also create a cubic with the tools of Rhino directly. Let me snap to points, so we have the same thing. So 1, 2, 3, and 4, and indeed we get exactly the same curve. So we are happy about it. So this was NURBS. We saw cubics, parabolas, so quadratic and linear, so lines. There's a couple of things more I wanna mention, which is let's use this this curve that was defined. We could do 2 other things. One is we could define a different weights for these functions. So if you go and check the curves menu here, let me define a curve with Grasshopper directly. So you see when you try to define a NURBS curve, it asks you points. So in this case, with the four points we already have. So let's take them in. Okay, multiple points. Right there. I'm not sure they are in the right order. So let me do it one by one. So 1, 2, 3, 4. Okay, now they are. So these are the points, and it asks you for 2 other parameters. One is weights and one is knots. So the weight is just a multiplier for these functions. So we may, instead of just writing this one, multiply, let's say, the second functions by 2, for example. Okay. So what you see is that by multiplying one of the functions by 2 or by a certain weight, this function has a greater impact on the curve. And indeed, if you write the same thing as in the weights here, that will work the same. So it's 1, 2, 1, 1. By default, they're all 1. The weights are all 1. Okay, so you can drop them in. And then it asks you for knots as well. In this case, I'll just write them by hand, or there's actually a component which creates the knots for you by giving the count, so which is the number of points. In this case is 4. The degree of the curve, in this case 3. And if it's periodic, it's false, it's not continuous, it's not a closed loop. So this is the knots. And indeed we get, I believe it's the opposite. So it's this one has 2. Okay, 10. Let's try different values. So it's not quite exactly the coefficients multiplied here, but it's having the effect of of increasing the weight of a certain knot. I'm not sure where you have to do the multiplication exactly to make a match, but this is what the weight is doing. And then the knots, if it's a vector, and it describes if the function is passing, how the function is passing through the points. So you see in this case is 0, 0, 0, 1, 1, 1. What does it mean? So let's bring it back to weight 1. What does it mean is that, well, we have 0, 0, which is telling him, it's telling him that the first point, it's actually a point where the curve has to pass through. And then 1, 1, 1 is representing the last thing up here, which tells it that it's passing through the last point. The other are missing, so they're not points which are used to pass through, but just control points that are used to control the shape of the curve. So these are all the parameters of a NURBS, and these weights are the reason why the function is called rational or non-rational. So if they're all 1, it's non-rational. If it's one of them is different than 1, then it's rational. And the non-uniform instead depends on the fact that this not vector may not be this one, so the simple one, but the curve may pass through the different points. So the speed at which the curve goes through a point, it's different. So the non-uniform parts depends on these knots, which define the clamping. So now we have also the understanding of what weight and the knots are. We know about the degree of the curve, so we basically know everything. We just need a small last step, which is extending this to 3D or to surfaces. We're not going to go in the same detail, but I'll just show you in Rhino directly this concept of the surface, because now that you understand control points, degrees, the weights and the knots, you can easily extend with your mind on how it may work in 3D, and you don't need to exactly know the math behind it. You already, by knowing these parameters, you can already control very well the NURBS, also the NURBS surface. So we will create a bunch of control points, which instead of holding a curve will hold a surface. Let's just move them around so they're not flat on the ground. Okay, and then we'll use this parameter in Rhino, which is just the surface from control point grid. So I'll just right click, and then it asks me how many rows are there. So in this case, I have 3 rows and 3 columns. And I have to change the degree because it's the same. If with 3 points, you can do degree 2. So I'll just do degree 2, and the points are now 3. And then the other direction, again, the degree is 2, and the number of control points is 3. And now it asks me for the point in order. So 1, 2, 3, 1, 2, 3, 1, 2, and 3. And indeed, we get a surface which is controlled by those points. And you can also visualize that by going to Surface Tools and turn them on, and you see indeed that you have the same thing that you have in 2D, but now you have it on a surface. Okay, and we can do the same thing in Grasshopper just before we wrap up. So there's a similar command, which is this one. If you go to Surface, Surface from Points, you can take the points. So let's take the attributes, so not parse string, the points. Okay, select multiple points. Let's select them in order so we are sure that they are right. Okay, and then U count is the number of rows in this case, so 3, and it will assume they are the same, and indeed, as in the columns, it will count the points you provide, and indeed you see you can get exactly the same result if you do it with Grasshopper as well. So this was basically it. So I hope you now understand a little more the NURBS. In the next episode, we will use this NURBS concept, both the curves and the surfaces, to create solids. Well, the surfaces to create solids. And what these solids are, they will be B-reps. And what B-rep is just many NURBS surfaces all connected to each other in a clever way so that they look like a solid. And you will see that the operations we'll use are just clever ways the CAD application gives us to create these control points and connect them in the proper order so that we don't have to do it by hands, because we could draw every single solid using manual defined control points, providing the weights, providing the knots, but it would be very annoying. So there are operations like extrusions, like lofts, sweeps, and stuff like that, and Boolean operations that you can use to define these surfaces in a more automated way, and use them for your design. So this was, I think, a useful theoretical background, so that you know what NURBS mean when you look at it and the different parameters that control it, and you can connect it back to some mathematical concepts that you may already be familiar with. So hope this video, you like the video. So leave a like, subscribe to the channel, and see you next time.